by Professor Veritennikov, who the affiliation is two places, University of Leeds and this Institute, International Institute, no, not International, Institute for Information
Transmission Problems,
in Moscow.
which is of course on Leeds.
His title is on filtering equations with non-specified initial data, and in this piece of paper, initial is not in parentheses. So probably he wanted to tell us something about it.
First of all, thank you very much for this kind of invitation. Yes, my intention was to add some news, and not only initial data could have been non-specified, but for this talk I actually did not manage this, sorry for that. So I will talk only about wrong initial data. However, more or less it's clear that the model may slightly change as well. Right. So I will try to concentrate on one particular technical hint, although I will do my best so to say, to make the talk non-technical. This is a joint work with Marina Kletsina. And this is the system, and I would like to leave it on the board. This is the signal, and this is observation. Two independent Brownian motions, everything multidimensional. Although for this talk, maybe I even assume that dimensions somewhere equals 1, but this is not important, except one special case where h may depend on y. But I think I will not concentrate on this case. So this is the system, and nonlinear filtering is so that we are interested in conditional measure. Given observations, the whole trajectory y, we construct optimal filter, which is a Bayesian problem. So if we know precisely the initial distribution of the signal, we can do, so to say, exact filtering. Now, what happens if we don't know exactly the initial distribution of the signal? There were already several talks on this topic, and this is just another attempt, one more attempt. So what I will try to explain, first of all, is what does it mean, especially in continuous time, not exact, not precise initial distribution. If you feel that it's enough, you just tell me and I stop. Because observations are given, and they somehow know about the initial distribution of the signal, right? So there was some evolution of the couple xy according to this system, and x0 has some precise initial distribution, say distribution mu0. And we observe that the whole trajectory of y. Now we pretend that mu is not known, and we replace it by some other measure mu 0. But observations are given, and they somehow remember about the initial distribution. So first point is that even for some unlucky initial distributions mu 0, we possibly could even claim straight away that it's wrong, and let's do some more accurate observation, measurement, so that the trajectory at least does not, how to say, does not contradict to this measure. Okay? So this is why, in particular, in many papers on the topic, it is assumed that, I will show some assumptions a little later. Often it is assumed that exact and non-exact initial distributions are equivalent. Because if they are equivalent, then how can we distinguish if we only see the trajectory of observations, which is realization of one omega, so to say. It should be okay. Right. So, yes. So what is a lucky issue is that it turns out that we can consider the problem as follows. We have our exact system, this one, xy, which I will denote by z. Exact system with initial distribution of the signal mu 0. And we can also consider another system, say z tilde, which is a couple of x tilde y tilde. Let's forget about given observations y for a minute. So x0 tilde has our new distribution mu 0. We pretend that this is what we know about the initial distribution of the signal. And so we have another couple. Now, for this new system, we can construct new filtering measure, which is our expected value of some function, say, or measure even x tilde belongs to something given trajectory y. T will be fixed. So I do not show it here, but this is sigma algebra from 0 to t, generated by y or y tilde, right? And so we are interested in this filtering measure. Now, pretending that we are given observations y, we would like to do the following. We actually plug in given trajectory y in this filter. This is what we're going to do. So I will use notation mu 0 and mu 0, well, I did not write down the similar filter for initial system, but it would have been mu 0 instead, right? Right, so how to plug in? It turns out that this expression is continuous in observations. We know that conditional expectation is always measurable function, but in this case, due to a rough filtering idea, due to Clark and Crisson, we can actually have continuity, so no problem to replace. And of course, even less problem in discrete time. and this is how we can replace, and this is, well, I skip some integrability, and this is this formula was presented many times already today and yesterday. So I will need some operators. I will need to introduce some operators, but maybe before introducing operators, I would like to give some example, which is not in my slides. So I will write down some example of conditions and statements. So the possible statements will be always of this type. We have our no, I need first some operators. Sorry for that. Operators are here. First bunch of operators is here. So by s sy, s with upper index y, we denote non-normalized evolution of measure mu, any initial measure mu, right? And by s, okay, let me show it here. So I repeat that mu sy is a measure, and it is given by integration of changed measure. Gamma is Girsanov exponent, and xt belongs to something, so this measure of something, times rho, which is gamma to the minus 1, right? Given y, given trajectory of our observations up to time t, integrated with respect to the measure mu0. So this is non-normalized evolution of initial measure mu, whatever this measure is. Now I will need S bar, normalized measure, normalized version. So we just divide this by normalizing constant, which is simply conditional probability, conditional measure, exact probability measure, conditional to y. What else? Yeah. So the theorem will always have the following form. We compare mu0 s bar given y. This is a measure, conditional filtering measure, and compare it with, well, actually, sorry, this measure also depends on initial measure mu0 because it's normalized measure. So in Bayesian setting, we should remember of exact initial distribution mu0. So this is mu0. We compare it with a wrong measure, similar operator given another mu0, total variation metric. Now this thing is still random. This is a measure, norm, the distance between two measures, but it's random, and we can take expectation given we have no choice given mu0, because precise initial distribution is mu0 necessarily. And so typical theorem is that this thing goes to 0 with some rate which can be, well, in different cases I will show different rates with some rate. Unlike in previous talk, I consider only ergodic situation. So the signal is always ergodic in some precise sense. It's homogeneous Markov process, right? And I will assume some assumptions which would guarantee some precise mixing or ergodic properties. And under those properties, I will claim that the rate of this convergence is exponential or polynomial or whatever. Okay. Now, this is the first set of operators. Okay. Yes, this S bar is normalized measure. And this is typical theory. Now, I would like to show some possible assumptions. But I emphasize that this is just example, and although in some our papers recently published, we formulate theorem under assumptions, under certain assumptions. Nevertheless, now I would like to emphasize that under whatever assumptions we can get certain mixing rate for the signal as a homogeneous Markov process which is ergodic. And then, in some sense, this rate of mixing will be inherited plus or minus epsilon in this theorem for the conditional measures. Okay, so for example, assumption 1 is condition on the drift B, and I assume that B of x, scalar product x, is less than some negative constant r, far from 0, far from 0. Wow, much greater than something. Okay. Or even the limit of this scalar product goes to minus infinity or equals minus infinity when x goes to infinity by modulus. This is first assumption, and it guarantees polynomial or better than any polynomial mixing rate in some special sense for the for our ergodic signal x. Second assumption is on the function h in the observations, and for simplicity now I just assume that it's C2 bounded. It can be relaxed a little. And the third assumption I mentioned already about equivalence of measures. I assume that the measures mu0 and mu0 are equivalent, and more than that, the density d mu over d nu is bounded. Plus, I need the last assumption, which is strangely without any A letter, but let me put A4. Both initial measures are assumed to have some exponential moment. Not any, but some. Again, this may be relaxed if finally, eventually, the statement is about polynomial convergence rate, then apparently it means that exponential moments can be relaxed to some polynomial moments. But we assume that with some constant C, mu0 and nu0 admit this some exponential moment. Okay, so under those assumptions, the theorem can be now presented more precise. Under A1, A4, we can say that the left-hand side above is less than some constant no, what is m? There is no m here, sorry. Some constant over 1 plus t to the k. Now what is k? K is some positive constant which exists. If we assume minus infinity here, then for any constant k, there exists such constant c, k, that this estimate holds true. If we assume only this part, then depending on r, there exists some k, such that this polynomial estimate holds true. And I wouldn't like to say more precisely, but roughly speaking, k is more or less linear with r, so kind of r over 2, I suppose, in this particular case of this simple system. So this is an example of the results, and now I would like to show some more technical tricks. Right, this shows stochastic partial differential equation, which is another possibility to understand how do we plug in observations into ROM, how do we incorporate ROM initial data. We can just think that we are solving this linear SPD given initial measure mu0 or given another initial measure nu0. That's it. It's another way to understand how we plug in ROM initial data. Now, what I need is some new notations. X and Z were already given, right? What is x tilde? X tilde is a new system with another initial measure nu0. Now, what is delta? Luckily for me, in the previous talk, there was explained that there is so-called mixing condition of on transition kernel, right? I think I have on some next slide. Okay, I can show it on the board. Of course, in many how to say, essentially we can forget that our time is continuous. After we applied a few times Ito's formula and Gersonov transformation, then we are just in position that well, we are studying some sequence of measures. By the way, I didn't show here t, and this is t. And we can assume that this t is just integer n, and n tends to infinity eventually. But during the calculus, this t or n will be fixed actually. So there will be eventually some estimate for any t or n. So let's think that our t time is integer for a while. Okay. Now we have transitions from n to next n to n plus 1, right? And we are interested in mixing properties of a conditional kernel, conditional transition of x given y from n to n plus 1. And we would like to have this, well, say, suppose q is this conditional kernel, right, from x to some next x prime. If we have, say, condition like this, with whatever probability measure lambda, and with some positive constant epsilon, this is a good mixing condition for this transitional kernel. I don't show why, but I mean conditional kernel. And by the way, there is observation that if we have this mixing condition for transition kernel which is non-conditional, then with the same constants it will hold true for conditional kernel. Right. So how to provide this mixing condition for transitional kernel? The matter is that in Hilbert, or another name is Birkhoff, in my talk I call it Birkhoff metric, there is contraction whenever we have this property, mixing property for transition kernel. So if we have contraction, we would apparently should have exponential convergence. And by the way, my theorem is not necessarily about exponential convergence. I can formulate exponential theorem as well. For that, I would need better, stronger assumption on the drift. That's all. So for non-conditional kernel, well, there are some. The matter is that transition kernels. Sorry, it should be x prime, of course. Transitions from different points x should not be singular. If they are singular, it fails. If they are not singular, we can just take one of them and use instead of lambda. Lambda is not necessarily big. It's any probability measure. So when do we know for diffusion processes that measures are non-singular? We know it, for example, due to Harnack inequality. It's a very good and very powerful method to provide mixing property for transition measures, for the signal and hence for the conditional transitions. Unfortunately, to use Harnack, we should restrict our signal on some ball or cube or whatever, or cylinder. So we cannot use it in the whole space. At least I'm not aware. Unless the whole thing is on some compact manifold. But we do consider RD, so which is not compact. So we would like to restrict our signals on some compacts. Now, if we do that, it looks like at some moments we may have mixing conditions when our signal is inside some, say, large ball. But otherwise, if it's outside, we have no mixing, or at least we don't know if we can control it properly. Okay. So the idea is that frequently, due to ergodic properties, due to this condition, say, our signal will be inside some large ball where we can use Harnack, where we will have mixing condition for the kernel, right? And if not, the feature, fine feature of Birkhoff or Hilbert metric is that it's a measure, it's a distance between two measures, but not measures actually, but between non-normalized measures. The constant does not matter, right? It's distance between rays, positive constant times measure, another measure times the same positive constant. Because of the definition of Birkhoff metric, no, yeah, this is the definition. If you imagine that you multiply both measures by some positive constant, in the right hand side will not change. So this is why for filtering, where we normalize measures, it's a great advantage to use this metric, because we can forget about normalizing. We may have contraction due to Harnack principle, at least from time to time, right? But with whatever kernel, if we have no contraction, at least it does not explode. There is no multiplier greater than 1. If we apply any transition kernel, the distance cannot be greater. So the idea is to arrange two sets of diffusions Z and Z tilde, right? And to wait until they are both in some large ball. Then we have contraction whenever they are both in both signals are in some large but fixed ball. Otherwise, we are not losing anything because of this property of Birkhoff metric. Right, but we started from total variation. Fortunately, there is a, well, with whatever constant, 2 maybe, but any constant would do here. We started with total variation, so we use this property to shift, to pass to Birkhoff metric, in which we will have frequent contraction. But what does it mean, frequent? How to measure it? The idea is just to say that our couples, both they're independent, by the way. I forgot to say that here there are Wiener processes W and B, but for this couple with tilde, I would use another couple of Wiener processes, which are independent of those. Okay, so they are completely independent. However, we are interested in measures, in evolution of conditional measures. Okay, now to show a little bit more, I need some more notations. And more notations are, I don't remember if I have those notations here. Yes. Yes. There is delta, which I will explain a little bit later, and there is, well, I need similar notations, S and S bar, on couple of measures. First, we had this mu S and mu S bar. So we have some initial measure, say mu, right? And we have some evolution due to some operator, normalized or non-normalized, which is called S or S bar, given trajectory of Y. Now, if we have a couple of diffusions, Z and Z tilde, we may try to follow the evolution of two measures, both. So let us, well, this is generic notation, mu and nu, but of course I mean to substitute mu0 and nu0 there, okay? So we have a couple of measures and similar notation. I don't change s to anything. I use the same letter. But now it means operator which acts on couple of measures for both diffusions, x and x tilde and y as well. Now every time when I write given y, I mean that we have y and y tilde, of course, and then we replace second trajectory by the first. So to say, it's given y and y again. Okay, so S bar is again normalized measure, and what is delta? Now let me show what is delta. Delta is a non-random vector of dimension n, and it consists of zeros and ones. And I mean to use 1 every time when both x and x tilde are inside some ball suitable for application of Harnack inequality. Okay. However, it's not non-random. So I mean that this one delta is a kind of indicator, of course. At each place j, I put 1 if both gentlemen, x and x tilde, are inside some ball, and more than that, actually our trajectory is continuous. So I would like the whole trajectory be less than some r plus 1. Right? And this is what I call dj. Initial values are inside the ball of radius r, and over the interval of time of length 1, they remain less than r plus 1, strictly less than r plus 1. So the idea is that due to ergodic properties of both diffusions, frequently we will have this indicator equal to 1. Now how it works then? I need, I think, last notation. Well, sorry for many notations, but this is the last one. Et given y and all those indices. What is Et? It's a complete measure. Of course, this is not a probability measure anymore, right? Because we have restriction. At some places we have ones, at some places we have zeros, but it's not the whole measure. So let's normalize it. If we normalize it, I denote it by S hat, last operator. S hat means a probability measure divided by its complete measure. Well, S hat is applied to initial couple mu 0 is of course probability measure. Okay. Now, what happens is now this is the main hint. We would like to compare the distance first without expectation. Of those two filtering measures, exact one and, so to say, wrong one, given observations. First observation is that, first remark, is that it's less than or equal to this difference, this distance. If we consider couples, it may be slightly more, but not less. Clearly, I suppose. I have some we have some about one-page calculus, because one referee was not happy with one line explanation. So, but it's correct. Now, from this line we go to this line just by normalizing. And very important and lucky fact is that, look, does it look like cheating? I should have used one normalizing constant Et for this term and another one for this term, because I changed the order of mu0 and mu0. It's some kind of symmetrization. Behind this, there is idea of coupling, of course. Coupling for just non-conditional Markov dynamics. But when we apply coupling for non-conditional dynamics, we always have probability measures. We have two processes, right, which evolve, but they have, so to say, full probability measure, both. Now, when we restrict our signals to some delta, why do we have the same measure for both components? So it's a lucky fact that both measures, these normalizing constants, are the same for both terms here. And so we can factorize. Now it remains, we split this whole sum into two terms, where the number of ones in delta, it's non-random split. Number of ones is less than some constant times n, and where it's greater than some constant times n. Now the idea is to say that if it's the number of ones is too small, see, whatever is the fixed ball which was chosen and it relates to this delta, whatever is this fixed ball, from time to time our process should be outside this ball, right? Diffusion, well, diffusion is non-degenerate, so from time to time it should be outside. So simply due to the law of large numbers, we have some limiting proportion of being inside the ball, right? And if this epsilon is too small, less than this proportion, roughly speaking, then this sum, I meant expectation, of course. Expectation and almost surely as well, of course. But here I meant expectation. Expectation should tend to 0 due to ergodic properties, due to law of large numbers. Now it remains to see what happens with the second sum. And with the second sum, the fact is that whenever, if we have so many, at least epsilon n contractions, we have exponential decay for the second sum due to this property of Birkhoff metric and above mentioned Harnack inequality. Right. So the second sum decays exponentially fast. That's it. So let me show a little bit more details. This is some stuff about constants of contraction. This is a little bit more details for this sum, for the first sum. So so to say, we have so many contractions, and those are normalizing measures, normalizing constants. Okay. So if we just replace all q to the something, this something may differ from term to term in the sum, right? But q to anything is less than 1. So if we just drop this q to anything, replace it by 1, we have this inequality, and now we can combine back all our normalizing constants to get this expectation. It's simply the sum of all indicators over this domain of indices. So we can replace it by probability that the number of ones is too small, and as I claimed earlier, it tends to 0 with some rate which I can estimate given this assumption or some other assumption. So this is how actually mixing estimates for signals can be used more or less directly to estimate conditional convergence, convergence of conditional measures. Now, last remark. Of course, this in compact case, this convergence is exponentially fast even without expectation, because on each step we have contraction. We don't need expectation on the left of this node. If we are interested in, say, discrete time, n, 1, 2, 3, and so on, we can use Barral-Cantelli lemma. So it's open question for us whether we can restrict our observations to some likely event to infinity and have this some convergence without indicator. But at least for discrete time, we can have non-averaged difference also tending to zero with some certain rate of convergence. That's all. Thank you very much.
Questions?
Oh, I ask always the same type of questions. For example, if you have a tracking problem, the initial condition is the starting of the target. Usually it's a delta function. You don't have a, well, the guy is not initializing the target with a nice Gaussian on some place. So usually the initial condition unknown is a delta function. So the assumption, no?
If it's delta function, well, do we allow delta function? Well, I can say that even if it's delta function, this value may be given not exact. You may not know exactly this value, this point where this delta measure.
Yes, you assume that the guy is somewhere,
Yeah.
and has been placed by someone, the Gaussian, for example.
Yeah.
But this uses Hilbert metric.
Yes, that's
So
why.
about
That's the main
mathematical
trouble with the Hilbert
Play
metric.
with
No. Yes, sorry.
Norms and so on.
I don't. No.
I don't.
Well, the matter is that directly this does not allow such atoms because we need density. However,
I think it's
however, if we do the first step and we have density after the first step, we can start just from the first step, not from 0 but from 1, for example. So this can be relaxed somehow.
there is a. We need the ratio to be bounded.
Well, this also can be relaxed to some LP norms, of course.
Or to a later time?
And
Not to the origin.
yes, and at a later time. The only thing is that somehow the trajectory should allow initial measure which is wrong. Maybe the algorithm will not run, refuse to run, if the measure is too different from what the observations expect.
I'm pretty sure that instead of using Hilbert projective metric, you can just put this out, this condition. I mean, the same tools will work. The coupling technique you have used will probably work because on a compact set you have contraction for the total variation. I'm not sure Hilbert projective.
The Hilbert metric deals with the normalization. Yes. You know, it eliminates.
Yeah, I know it helps, but we can do the same with total variation norms.
Well, possibly.
More questions? If not, then let's thank all the speakers.
Thank you very much.